the synchronization phenomena was discovered or first recorded by Huygens, so a Dutch physicist. The story says that he was sick in his bed and he was looking at the two pendulum clock he had on his wall, and they, no matter what were the initial condition, they all synchronize. Okay, so oscillate together. So he tried to reproduce the experiment. I think it's a drawing from him, um, and also see the synchronization phenomena. So here is the experiment with more oscillators, more clock, let's say. So it's metronomes. They all start at different phase and angles, and you see it's, if you listen to the noise, it's very noisy. Okay, there is not one noise, and they are on a plate that basically provides some coupling, some interaction between them, because the plate is reacting to the phase of all these metronomes. And if we go at the end of the video, you kind of see they are almost all synchronized now. There is one noise. There is still some that do crazy stuff, but basically they are all synchronized while they start at something very noisy. Okay? So now, the question, if you are a scientist, is it a generic phenomena, and why does it occur, and can we describe that with the minimal ingredient of dynamical systems? So basically, the motivation is that this phenomena is widely spread. So fireflies, for example, that can apparently flash unison, crickets, they sing together. When there is a crowd that upload, they basically always upload together, or kind of in synchrony. Then there is a biological phenomenon. Epilepsy, you can describe it as some kind of synchrony in the neuron, and basically it provokes this epilepsy. There is also in biological rhythm, pacemaker. There is laser in physics. There is many application in engineering. You also have the current you have is 60 hertz in the US at least, and it's all generator that are kind of synchronized. So it's very widespread. So you need some kind of description, very simple, and this was provided by Kuramoto. Um, so in the 70s, and basically the model requirement, what you want your model to satisfy, you want n oscillators. You want them to be independent from each other in the sense they are self-sustained, so they have their own natural frequency, but there is also an interaction between them. Okay, and basically wrote what we might consider the simplest model of coupled oscillator. So this omega here is different for every oscillator, meaning that they have own their natural frequency of distribution. If you think of a crowd that clapped, you have a different frequency of clapping than your neighbor. Okay, but you can say it's very close, maybe, and you can say that this omega I are drawn from some distribution J that you know. And plus a terms here that is a coupling term. And the simplest coupling you can think of is a sine coupling. So if the two phases are equal, then it's zero here, and sine zero is zero. So it means that it will, these terms, and you see there is a sum, meaning that it is coupled to every other oscillator of the network. And K is a coupling constant. So basically, if this term will favor that all oscillators have the same phase, but at the same time they all have different frequency. So that's a battle between the two. And you of course here you have the theta is the angle, the phase of the oscillator, and you see the dot because it's a dynamical system. But here it's n dimensional. You have n equation. I just wrote a compact form, but you have n. So the question is what is the dynamics of that? Is there a critical K after which you have synchrony? How does it work? Is there a bifurcation? Bifurcation meaning after this critical K you have synchrony. Um, what is the effect of the dimension if you have just two oscillator, three oscillator, n oscillator, and an infinite number of that? And how can you study a very large system? Because we already see for three dimension, it seemed very tricky already. So for n, it might be impossible. So now just let's see the basics of this model. You can define a synchrony parameter, which is called R, and basically it has the phase of every oscillator. So you don't need really to understand that, but what you need to understand is here is the oscillator on my on a circle. In fact, they are doing because it is phase, it is 2 pi, so each oscillator is doing circle. You imagine if you have a process, periodic process, you can represent it on a cycle like this. And here are all the oscillator. And here they have some coupling k equal 1. And you see they are uncoupled. They are unsynchronized. They are coupled, but not enough because they are unsynchronized. And basically this R, which is a complex number, is represented here. Okay. So here it is almost 0, okay? Now, if you have k equal a larger number, you start to have synchrony. You see there is a huge block that is synchronized. So they are all clapping in unison if you think of a crowd, but some of them are not clapping with the rest, okay? And if you look at the R parameter, it is non-zero. It is something, okay? And the phase of this error parameter evolve with the mean phase of the whole ensemble. And now complete full phase locking is when every oscillator is locked together. And here the R is almost 1 if you compute it. I mean, the absolute value of R. Okay? So how to study that? So here I will introduce the infinite dimensional system. So if you have this n equation of coupled oscillator, here I wrote a more explicit form. Basically, you have what we call the n-dimensional system because you just need n initial condition to get your system started. Okay? So it's an n-dimensional system. But as I say, it's not easy to study. You cannot study in general for every n what happened to the dynamical system. So what you want is to study the case where there is an infinity of them. Because in this case, you can do something. When they are very large, you can study. So the idea is to have a density function f at every time. And how evolve f? What is the dynamical equation for f? Now it is so here it is so now the question is how f evolve with time. And in fact, f will evolve according to this type of equation. So it's called a partial differential equation because now the evolution in time is just you have to do a partial derivative because x has f as other variable. Now the question is how f evolve in time. So the equation that f follows has kind of the similar form. So here is the derivative with respect to time, but you see there is a partial derivative here because f depends on other variable. So that's why we put a partial derivative, this symbol. And it is equal to some function, k curve. I call this k curve, okay? Or fancy k. And this is not a standard function. It is not just, it will not just square f or what. It can do that, but it can also derivate f, etc. So we call that a functional operator, okay? So now, why do I say it is infinite dimensional? Because now, you remember here, the initial condition is just a vector with n component. Now, the initial condition at time 0, I need a function of theta and omega. So if you think in terms of points, how many points do I need? I need a continuum of points. So an infinite number of points. So that's why the dimension is infinite. So to translate what we just did, so the idea here, instead of studying an infinite number of equations, when you are interested in the large limit of the number of oscillator of coupled equation, so these are called ordinary differential equation, or ODE on the left. Okay, we now study one partial differential equation, which is abbreviated with PDE. Okay, so we go from, instead of studying an infinite number of these, we study one like that. So it might seem like a good trade-off, okay, because we just have one equation. So of course we have less information in that trade-off, because now we just have a density, so average quantity basically. We don't know which is what, which is doing what. Okay, but why not? But also now we have a partial differential equation, and in general, partial differential equations are just more complex because there is more variables. Okay, but as you will see, we can still have some good result. And typically one thing we lose is the geometrical interpretation we had before. Now it will be, let's say, very much more difficult to interpret to interpret this in terms of trajectories. You still can it somehow, but it is less straightforward than the cycle we had before with prey, predators, etc. But yeah, as you will see, the spectral analysis is what is really common to both approach. So for the Kuramoto model, if I write the equation, now f is my density of oscillator. Here I just explicit this k for the Kuramoto case. Okay. Here we have what we call the advection operator. So basically this operator is translating this part, the fact that every oscillator has its own frequency and evolve with it. And this term is the interaction term. So you recognize the sign, but now it's average over the density. Here I do not specify the integral, but the bound is 0 to pi for theta and minus infinity to plus infinity for omega. And you recognize this term was this interaction term. Okay, so already here you kind of think, oh, this might be a very difficult equation. And you see there is a nonlinearity. There is f times f here in this term. So it means this all partial differential equation is nonlinear. And these are the most difficult. So there is some condition on f. The average over all the angle has to be the distribution of all the omega, okay? And it has to be normalized somehow, okay? Now, remember, if we want to do spectral analysis, we want to find basically a steady state of this equation. Remember, so we steady state is still this term equal to zero, so we have to find a solution of this. So in fact there is one trivial solution which has a physical meaning. It is the unsynchronized solution. So if my function f does not depend on the angle, you can verify here this term, because it's the derivative with respect to the angle, is zero, and here it's a similar thing happened. So, and to respect the normalization condition, I have to have this function. So this is just a steady state. And if I compute the order parameter, remember that measure synchrony, it is zero in this case for this in steady state. So this steady state is in this steady state all the oscillator are unsynchronized. So now if we want to perform linear stability, we take this f, this stationary state, and we give a perturbation. And now we look at the linear operator. So now we'll write linear operator of this function f like this. And you can verify or not that it is as this form. Okay. So now what we do, we want to find the spectrum. Wait, do we know how to compute the spectrum of that, the eigenvalues, etc.? And another question is it the same as in the finite dimensional case? So the answer to that will be in the next lecture, okay? Next part, so tomorrow, I guess. And so it's finished for today. I hope you enjoy it. It's kind of weird to talk to a computer alone. So if you have a remark, you can send them to me. Thank you.